and often reinforce each other, but indeed you can have one without the other. The other thing I'll say to all of you today is that, especially here in the US, this is relevant. Political forces and what I would call geopolitical swings, pendulum swings, they do matter and they affect our lives, but they do not control Mother Nature or changing global conditions, nor will they ultimately govern the future of sustainability related initiatives. Human necessity will drive and govern. I point out that Europe is the leader really currently in sustainability related awareness and significantly policy. They are creating laws and policies that govern the new infrastructure, and we're learning from them. When I'm active in standardization committees, much of the sustainability work is through the European norms and also ISO. So there's constantly new developments in the space. We all need to be educated. We all need to pay attention. What you're seeing here is a chart from the National Oceanic and Atmospheric Administration. It shows us the cost of recovery, adjusted for the Consumer Price Index. The cost is increasing because the frequency of natural emergencies is increasing, such as floods and fires, superstorms, droughts. Our weather is changing, and its subsequent stress on our infrastructure is increasing. This is happening while the global trend towards replacing fossil fuel cars with electric cars is intensifying our thirst for needed metals and driving a growing mining industry. Your cell phones, your cars, we're electrifying our energy sources, and this requires a lot of metals. Electric cars result in a heavier vehicle that are were never designed challenging our infrastructure. I don't know about your town, but in my home here in Austin, Texas, there's been an increase in Waymo cars, driverless cars. And according to Texas transportation officials, the next step in this linear process is to have automated transport lanes, which much less lane wander, called lane keeping. And this also increases localized stresses on road structures, roads that indeed were not really designed for this. So there's 30 to 40% more rutting associated with lane keeping and close to 3 times more fatigue failure or cracking. And cracking is not good, right? This leads to water intrusion and related degradation mechanisms. This is an environment of underfunded maintenance, as reported by the USDOT. You see here the report card, the recent report card on United States infrastructure roads. I would also add that an application for that's very impressive scale is sediment pollution, and this is worldwide. This is a global issue. We, human activity, drive this pollution, and the damage caused is very expensive to our society, as you see here. The effect of erosion to waterways is also harmful, driven largely by warming water resources, the choking off of dissolved oxygen supply, the increased turbidity. These changes fundamentally challenge our ecosystems, including accelerated loss of wetlands. Important to coastal erosion prevention. Here, we see the warming of the upper 700 meters of our oceans, right? With warming atmosphere and warming oceans, the ability to hold and eventually release suddenly historically high concentrations of precipitation is significantly increased. And this is stressing not only our roads, but our traditional erosion control solutions. So we need a different way From an engineering perspective, this means an added design criteria. As my good friend Dr. Jorge Zornberg has expressed, most engineering students early in their collegiate career learn about materials and learn about the performance of those materials. They graduate, they go out into the commercial world, they quickly learn that economics governs decisions on firms, decisions on materials. But now we're starting to figure out that there's a very strong, urgent need for the requirements for sustainability and indeed resilience. The United Nations, of course, most of you have seen this, has set the stage for humankind to target sustainability with these 17 goals, ranging from food security to an end of poverty, but also a response to climate change and the preservation of clean environments. But sustainability and resilience means different things to different people. There's often in design a push-pull relationship between economic concerns and equity, human equity or social justice, engineering efficiencies, and the lowest carbon footprint, right? Geotechnical and civil and environmental geologic engineers are starting to navigate these kinds of push-pull issues in their design. Indeed, a given structure, geotechnical structure, is burdened with requirements informed by or affected by multiple considerations: carbon counting, economic cost, public benefit, resilience or future proofing of a structure. Ivan Damians, the current chair of the IGS Technical Committee on Reinforcement, compared three wall designs: a gravity wall, a cantilever wall, a geosynthetic reinforced wall. He used MIVES, which is Spanish, Spain, an integrated value model for sustainable assessment, having a multi-criteria decision-making methodology for evaluating sustainability. And what's interesting about that is when he plugged everything in, all the data was plugged in and played with the weighting of all these sustainability related considerations, not just carbon counting, then the answer changed, right? The best option changed, showing that true sustainability assessments require a holistic consideration of many considerations, several parameters. So it's clear now that sustainable and resilient design are important as we experience warming of the atmosphere as well as water resources, the redefinition of extreme weather-related events to intense droughts, flood storms, and we're inviting infrastructure development industries to embrace more resilient and sustainable designs using more resilient and sustainable materials. And the other thing I'd point out is that it's in this planning and design phase of the development process that we have the greatest impact on making a change in our infrastructure development. For example, if I'm building a building foundation project, there can be a choice of foundation types at the planning stage, while the choice is limited to those materials during the design phase. And in the execution stage, the choice is very limited to just the equipment used to build my project. So it's really important that we maximize the benefit of these changes in our design to articulate sustainability, move towards sustainable and resilient considerations early in the planning and design phases. I'd also add that, if we're thinking about design materials, construction materials, what about aggregates versus geosynthetics? Aggregates of adequate quality for construction are among the less renewable resources on Earth. Eric Blund, my good friend, pointed out that just in the last few years, this wonderful building in Dubai, this tall, record-setting building, the Burj Khalifa, 110,000 metric tons of concrete but it needed a component with a very strong specification for the sand that was not available in a country covered with sand. And so all of this sand was transported and imported from Australia. Um, so this is an issue, right? Sand and gravel, they're very durable when they're not contaminated, certainly. Aggregates and sands are known commodities. We study them in school. We have designed with them for centuries, but indeed our needs are changing as we grow in population and in traffic. So again, in my own town of Austin, Texas, when I moved here early to go to college in the early 80s, it's been nothing but a solid boom. This is Texas. Economy's on fire. People are moving from all over the United States into in Houston. All those people bring their vehicles. All of the infrastructure that we have is inevitably going to not be enough, right? And while our needs increase, the availability of aggregates, competent aggregates to build road widths, remains the same. It's not increasing. So see if I can move on here. Seem to be stuck. There we go. Okay, so let's talk a little bit about geosynthetics. For the not initiated, what we're talking about here is materials that are artificial product to Earth to fulfill a function, right? In whichever function they're used, the geosynthetics will either permeable or impermeable, allowing for or preventing the flow of liquid or gas in either direction. In general, geosynthetics are in the form of textiles. And when they're in the form of textiles, they're permeable. They can be woven, as in the picture here, or non-woven or knitted. They're used with a range of related products listed here. They're really the workhorse of geosynthetics with many, many different functions. Impermeable geosynthetics typically perform a barrier function and are often in the form of a membrane. Here you see some pictures of small samples of geosynthetics. Most of the main types of geosynthetics, what's probably not shown here is geofoam, polystyrene blocks, and drainage noodles. But you see here geotextiles, geogrids for enforcement, stabilization, geomembrane barriers, geosynthetic clay liner barriers, geonets, and composites, of course, when two geosynthetics are joined together. In practice, geosynthetics are typically applied across a very large area, as in these examples showing a geocell on the left and a geogrid on the right. The geocell is filled with soil or aggregate, which confines it. It holds it in place, preventing particles from moving laterally, creating a more stabilized base, right? A geogrid on the right reinforces an unbound layer or strengthens an unbound layer of aggregate, such as asphalt, leading to an increase, a longer service life of that road, an increase in performance and service life. So geosynthetics offer a wealth of properties, right, that serve their applications. I'll also add that as manufactured products, they differ from soil and aggregates in that they are highly controlled, produced under maximized manufacturing conditions, highly engineered formulations. They're characterized by a high degree of consistency, serving a more stabilized construction, more certified construction, if you will. For those being introduced to geosynthetics design and application and materials, the IGS has just published geosynthetics handbook right alongside handbooks for structural steel. Now we have a very first edition of this. Significantly, this is an application-based manual, a handbook, full of information about the utility of geoscience and resilient design. Pick geologists, engineers, non-engineers, all very easy to read, very easy to conceptualize and to absorb information, full of figures, providing the enhanced reader experience, if you will. This is a very important contribution to the geosynthetics and geosynthetics awareness initiatives throughout the design community. It's available at the IGS website, and certainly, Dr. Reddy, every university should have this on their bookshelf, this book. So with geosynthetic defined as a compelling construction material, and as a construction material, we will their carbon footprint, right? Their environmental carbon footprints. Let's think about how we do that. We determine the carbon impact of using geosynthetics as material, compare with other materials. You see with columns assigned to various stages of construction work, from raw material production to production manufacturing to shipping to installation. We see end of life, the life cycle, the full life cycle of this product. Any product for that matter. Here's a brief overview of these steps of evaluating this carbon footprint called the life cycle analysis, defined based on project characteristics like paved roads, 1 kilometer long and X meters wide, for Y traffic conditions, for a landfill, for 1 square meter of a drainage product. What is that situation I'm looking at? Each different material choice in a design alternative will have an index, and there are method software packages and databases to assist us here. So here, a functional unit is that little unit that I'm evaluating, comparing different design approaches with. A functional unit is a component or a service with a clearly defined role within a larger system. So it represents a quantified performance of that system, and the definition depends on the context, the life cycle assessments. It is a reference unit for comparing products by their function, right? We need enough detail with a functional unit to provide a valid comparison with other material alternatives. Like you see here, I could plan on a pile, a massive pile foundation without a bearing capacity failure for a factor of safety of 2, no greater cost than X USD, and installed in no less than X time, right? So now I can start looking at alternatives to provide that function, that service in my design. Now, note that the language of carbon counting is always through the use of carbon equivalents. What is this? The CO2 equivalent is a unit that standardizes the climate impact of different greenhouse gases by comparing warming potential to carbon dioxide, sort of the common denominator. To calculate it, you multiply the mass of the specific greenhouse gas by its global warming potential relative to CO2. And this provides a single comparable metric for the total climate impact of all greenhouse gas emissions. Very important tool that we go. So let's just play with this. Let's take 1 kilogram of concrete, and I know all the components of my concrete, and consider the inputs and then the resulting emission outputs. If I get that, then I can multiply the emission factor in a carbon equivalent unit, right, a CO2e unit, times the mass of the concrete shown here for carbon dioxide. So that 1 kilogram will generate 149 kilograms of CO2. And then I would do that, I would repeat that calculation for other emissions. So this is how I compare these different materials. But that's material carbon counting. What about the shift of that material to the site? And this is a function of the type of road and the distance I'm traveling. The paved road is not the same as the unpaved road, right? So these go into our calculations. Also considered is how full my delivery truck is, its efficiency, its fuel efficiency, its weight, a lightweight truck or a heavy truck. Now, a lot of this carbon counting and shipping data can come from what we call environmental product declarations. And these are produced by equipment manufacturers, by material manufacturers, geosynthetic manufacturers, and then they're published by these same companies. So a lot of this information comes from them. What we're still missing in our industry is this, the life cycle index associated with construction. It's leaning into equipment published EPDs, but they're so active here. Carbon footprint is related to consumption and efficiency of installation and construction. That efficiency we need from some of our geosynthetic installers, and really, for that matter, acting community. Factored in are the power of the engine, loading factors, fuel density and efficiencies. All of these things go into considering the carbon footprint of construction. And then we consider the operation time, which depends on workloads and productivity rates, something called the bucket fill capacity factor, right, comes into play. How many trips am I taking to the fill capacity? How many trips do I have to make between the stockpile of material and the compacted fill location or the installation location? This is all to point out that these are not just numbers, but significant calculations that impact the environmental carbon footprint application. And why is geosynthetics industry, why are we so keenly aware of this? Because the use of geosynthetics is a significant solution to lowering the carbon footprint of transportation, shipping, and installation. Not just an economic benefit, but a sustainability benefit as well. So when we can replace a lot of these drainage blocks with a roll of geocomposite drain, that's a big issue, right? That's a big contribution. When we eliminate these significant numbers of transports, ships or trucks at lighter loads, then we're giving numerous sustainability benefits, including less tire wear, less fuel used, less time invested, all with a lower carbon footprint construction material. So again, I show you this to draw back the curtain on the process and calculations of sustainability. Meanwhile, there are many online platforms and databases to assist you in finding carbon footprints associated with construction materials. The challenge with many of these platforms, though, is that many of them, if not most of them, do not include geosynthetics information. And for that reason, the International Geosynthetic Society partnered with One-Click Life Cycle Analysis, or One-Click LCA. And what we did was we brought geosynthetic materials and their applications in different components, different platforms, if you will, to be included on their program for comparing different construction materials. One-Click spends most of its time going around planet Earth and harvesting these environmental product directives and their associated material carbon scores. They are a very important layer in sustainability education and resource development associated with sustainability and resilience. So they provide an application template that really was developed by our team at the IGS. They assist geosynthetic manufacturers with EPD development and publishing. They are carbon experts at LCA. So let's look at a couple of comparisons here. We're comparing here a functional unit of 1 square meter of a landfill cap, a drainage layer built with a drainage aggregate or produced with carried out by a geocomposite drain, asking for service life of 100 years, right? So note that even the drain has a geosynthetic filter and protection geotextiles as part of the design. So what we can do is we can plug in this information. Calculations are seen here, including considerations of transport lorry or truck is included here, or freight rail, depending on the material. We're we're integrating here with global on the one-click platform for quickly adding public EPD information and generic data. And what we come out with is a visualization of a lower carbon footprint, right? Results based on the stages of the life cycle analysis that we saw, right? Are we looking at the raw materials or the shipping, the production of those materials, the shipping of those materials, the final waste disposal or recycling of those materials? And you see in the case of the geosynthetic drain, we have a lot of advantage in the context of geosynthetic stabilization. We can also look at in the context of the material, right? The shipping material and the gravel or the geotextile or the composite, the components, the material components of those CO2 equivalent scores. We have a lot of these applications on the one-click platform, from landfill linings to landfill drainage courses, canals. We're looking at road stabilization applications, steep slopes, retaining walls, just all kinds of applications for an engineer user. Now, the EAGM, this is the European Association of Geosynthetic Manufacture, conducted life cycle analyses for many different applications, including geosynthetics versus traditional solutions, if you will, non-geosynthetic designs. They considered 8 impact categories and found filtration functions achieved around a 90% reduction in carbon footprint and over 80% savings in primary energy demand. A retaining wall savings were over 80%. Landfill drainage carbon savings were around 65%. Foundation stabilization was over 30%. Really impactful advantages, right? A survey of 25 applications demonstrated an overall average of a 65% reduction in carbon footprint using geosynthetics, right? Very, very impressive in the context of using geosynthetics as a product. Okay, well, now let's take a look. That's a big, long preamble, right? And a little bit of information about geosynthetics. But let's take a look at these applications, right? Let's look at a few applications. These are just common applications that are used for. And I'll start a little bit with erosion control. Erosion control, these are synthetic materials, right? And they can include very high strength load-bearing components, multiple layers, sometimes including a geogrid or even metallic components, as you see in a picture here, to assume load on steep slopes. And these products are providing surface erosion control as well as slope stability, all while lending their porosity to vegetation. The best erosion control is vegetation, right? But vegetation alone can be enhanced by these geosynthetics because the vegetation root structures can become intimately entwined with the porous structure as reinforcement to their root structure. The root structure is now not just within a soil matrix, but an established anchored 3-dimensional structure for us. And this is very important. And this, of course, provides us with a lot more benefits for longer term healthy vegetation stands. Also important is the benefit of aesthetics, right? Many countries design solely for green slopes and walls. Their weather promotes that vegetation growth, that vegetation health, as long as the vegetation is strong and reinforced, if you will. Other benefits include reduced thermal absorption, hydrostatic pressure relief, pore water pressure relief, and of course, reduced flow velocities. So really nice application, very strong application of geosynthetics. These turf reinforcement mats assist where concentrations of hydraulic flow are very high, right? And velocities are very high, including shoreline slopes that undergo constant erosive forces. So very important application. Reinforced vegetation, again, enables design for additional hydraulic stress. So the reinforced root structure prevents the dislodgement of root structures in vegetation, keeping their reinforced slopes intact. Scour is another big issue in infrastructure and hydraulic infrastructure, and this occurs when there's a high velocity, fast moving water around these bridges, right? The bridge removes sediment from around the bridge column foundation, leaving behind scour holes. And these holes, in turn, can seriously compromise the stability of the column's integrity. So, what do we think about that? The geosynthetic response here consists of two very important components. First, isolating a support system with an appropriate design geotextile filter suitable for dynamic hydraulic stresses, as well as an armor layer working to stabilize the column and prevent adjacent erosion or scour erosion. Scour protection of columns and support piles with geomats and geobags filled with on-site soil is very common and adds resiliency to the column and lower carbon footprint, as I can use local soils, indigenous soils, to fill these bags. Let me turn now to a novel use for barrier geosynthetics, such as geomembranes, turning now to mining applications. A novel use of these materials, not just for the very important application of environmental protection, right? Preventing contaminated pregnant solutions, the result of leaching from going to a water table, from contaminating that water table, but also as these covers that prevent rainwater dilution of the digestion process while elevating the reaction temperature of these digestion processes for increased yields of metals. I mean, this is really nice. This is a chalcopyrite case history that was leached at an increased temperature, resulting in more yield and faster yield for better economics. Also afforded the use of facilitated by the use of a geomembrane raincoat. Now, in this environmental application, of course, I need to point out that in this highly regulated application, regulated by here in the U.S. By the U.S. EPA and all over the world, really in many different environmental authorities, landfills or waste containment, both municipal solid waste and hazardous waste, have represented a significant user of geosynthetics, including base liner systems, as well as covers when landfills are closed. So the barrier function, the enforcement function, increased slopes, steepened slopes means more fill available, covers, erosion control, drainage pipes, all kinds of different geosynthetics included in this very important application. In 2002, Dr. David Daniels, Dr. Bob Kerner, with Rudy Bonaparte at Geosyntec Consultants, received a grant from the US EPA to grade the performance of landfills, right? How are we doing constructing our waste containment infrastructure and measuring the leakage rates from geomembranes alone to clay and geomembrane composites to composite systems that consisted of that composite lining systems with a geomembrane and a geosynthetic clay liner. And they saw them through the initial filling period with waste, subsequent filling material, and then after final cover, what's the grade do we have in protecting that water table by measuring the leakage rate? And you see leakage rate both in gallons per acre per day and liters per hectare per day. And the power of this composite lining system is clear, right? A very good report card for landfill technology. So in roads, the use of geosynthetics solve many problems, such as frost heave, wetting and drying related to displacements, the mechanism quite often for road degradation, the displacement of those aggregate layers beneath the pavement, the use of imperfect or non-desirable fills. Geosynthetics can help with that, as previously discussed. Increase traffic loads, right? Increase as a function of electrical vehicles. They can also reduce the amount and expense of structural fill that you see here while preserving the integrity of the layers, eliminating degradation through mixing. So many contributions of geosynthetics to road infrastructure. I'll go back to mining, right? Mining haul roads represent a dynamic case history, if you will, with heavy and dynamic loads and safety considerations. Very challenging for this. This is a little case history. This is a Brazilian diamond mine with a problematic haul road. This is their original road design, resulting in problematic slowdowns when rain occurred. Over 2 meters here of designed road structure, right? 400 tons, 650, 800 trips per day. This is a big problem for them. Why is it a problem? Because every time it rained, the effective rain on the transfer of produced yield came to almost a halt, right? Rain would slow traffic down and cause financial and efficiency loss. I mean, these mining companies are driven by the financial world, right? The price of these metals, the supply and demand, and our demand has never been higher. There's no time to slow down, right? When there's such high demand. So this chart shows the relationship of the rainfall frequency and average speed of the delivery trucks, and you see that the mine is not very happy at all here when it rains. So what's the solution? The solution was the use of geogrids to stabilize a sandy gravel cover and a gravel cover and a sandy silt tailings layer. The use of a separator geotextile to keep the integrity of these layers there. So both a stabilizing layers of geogrid and a separator geotextile, and the road is competent and it's fixed even when it's rained, because the gravel doesn't hold any pore water pressure and lets the water out freely. There's efficiencies, the financiers are achieved, and everyone lived happily ever after as a function of a geosynthetic solution. So when managing waste, different treatment options show considerable variation in emissions, right? So geosynthetics are an essential component, as we just talked about, of responsible disposal through a composite lining system. And this chart shows greenhouse gas emissions of 1 metric ton of plastic utility, right, across the life cycle. And estimates show that landfill disposal results in lower greenhouse gas emissions from plastic waste by 42% compared with open burn, 28% savings compared with incineration, and 23% reduction compared with compostables, right? So again, there's all kinds of ways to slice this carbon footprint benefit story. If the cement industry were a country, it would be the 3rd highest emitter of carbon dioxide globally. If from the manufacture of cement, with 1.6 billion metric tons of carbon dioxide in 2022, right? In the US, the cement industry also emits over 500,000 tons per year of harmful sulfur dioxide, nitrogen oxide, carbon monoxide. Use of geosynthetics greatly reduces carbon emissions and energy use in the following ways, right? So this is very important. Geosynthetics make infrastructure more resilient. This picture shows geosynthetics embankment with seismic resilience for highway in a Chinese Taipei in Taiwan. If the soil in the area where you would be adding a dense load, right? The pressure will force the soil to warp. And so geosynthetics help secure the soil, making it more climate resilient and resilient to earthquakes, resistant to earthquakes and other hazards. In regions prone to hurricanes, it's especially important to have robust access roads along power transmission lines to allow quick and safe repair, right? To restore power to communities that might otherwise be without electricity for days or weeks. You hear stories about that these days, right? Where an island without electricity is without electricity for weeks because of access to these power lines, right? Ground movement is a major cause of cracking in concrete lined canals and leading to significant water loss. Geomembrane barriers can also prevent this, a composite lining system in that canal. So we save natural resources. We've talked about that, right? Construction aggregate consumes a mass equivalent of about 4,400 Empire State Buildings. In a single year in the United States alone, geosynthetics replace significant quantities of high quality aggregate. Use of aggregates can be highly problematic in terms of energy and wider environmental considerations. And depending on geology and planning restrictions, suitable construction aggregates are unlikely to be available immediately adjacent to construction sites. So geosynthetics play a very beneficial role with all of these challenges. This picture shows geosynthetics to filter sludge, preventing harmful materials entering water systems. When heavy trucks are used to transport aggregates over long distances, this produces substantial tire wear in the form of microplastics, which then enter waterways through road runoff. Use of geosynthetics greatly reduces road haulage requirements. So geosynthetics are used to line tailings dams, store toxins such as heavy metals. They are used in mining as barriers to prevent these toxins entering rivers and groundwater. In landfills, we just talked about landfills. Geomembranes are used to line the landfill to prevent toxic seepage. So I'm running out of time here, and I want to leave a little time for questions and answers. But let me just say, geosynthetics are compelling. I would highly encourage you to get involved, to learn more about geosynthetics, pick up the handbook. But significantly, it's a very low fruit to join the IGS North American chapter here in the US, the Indian chapter in India. There's IGS chapters all over the world. You can go to our website and learn about them. And the reason you would join the chapter is because you become aware of their many events, and especially they're hosting, the North American chapter here is hosting the 13th International Conference on Geosynthetics in North America, in Montreal, in Canada. And this is not very often, right? So it's for all you North Americans, it's right in our backyard. And it's the perfect opportunity to attend, join the IGS chapter, network, and network with many geosynthetic professionals. And that includes over 3,000 industry peers, access the conference proceedings, receive geosynthetic journals. There's a monthly newsletter, there's free webinars like this, conference discounts, and so forth, many benefits. I would also, in the world of sustainability and resilience, I'd invite you to consider joining the IGS Sustainability Committee. It's open to all IGS members. It meets monthly online. We just had one the other day, a wonderful meeting. That IGS Environmental Sustainability Calculator is one of their products. They contributed to the IGS handbook. You can network with peers, help shape IGS resources to support members to practice sustainability. Enter our case history competition, demonstrate to your clients your commitment to responsible business objectives. And with that, Dr. Reddy, I will end. A little less than 10 minutes left, and I am open to entertain any questions that you might have. Hopefully this was gave you a little bit of information about geosynthetics contributions to resilient and sustainable infrastructure.
Very good, Sam. Thank you very much for your very comprehensive presentation. Let's take care of a few logistics first, and then we'll get back to question and answer session. So first thing is, the link for Google form link is posted in the chat box. So you must fill that form in order to get the certificate. And the second thing is, let's, if it is possible for you, show your video so that we can have a screenshot of all the people that are attending. So hopefully, let's see. Okay, can you share the screen now? Can you show? Okay. So let's see. I mean, our presenter can see the faces instead of just looking at the names of the people. So we'll just give a few more seconds so that we can have everybody open their video, and let's see if we should be able to capture screenshot without these comments. Okay. And we give okay 10 more seconds before we let everyone. All right, everybody got their videos on. So everybody look into the camera, give a big smile, because as I told everyone, I tell every time that everyone who attends these webinars are happy people, right? So look into the camera, give a big smile, everybody. All right? Got it? Jagdish?
Yeah, got it.
Okay, all right. Thanks, everyone. So at least I will share these pictures on our WhatsApp group. So if you want it. And Sam, again, thanks again for your elaborate presentation.